to the organizers for putting this very interesting conference together and for their invitation. So I'm going to talk about high-dimensional robust regression, and essentially it's a way to revisit some very classical problem in statistics, but that perhaps gives us A, some insight about what to do when we have high-dimensional data, and B, some insight on old classical problems, even in the low-dimensional case. Okay, and we'll see how to pick the loss in high-dimensional regression, which seems simple, but perhaps is a bit surprising. Okay, so the first thing I'll do is just set up the notation. I consider a simple linear regression model. Okay, so I have yi, which is my response, is in R, is xi transpose beta naught. Xi is a random vector in Rp, beta naught is a vector in Rp, and epsilon I is in R. Okay, so I want to estimate beta naught, its regression. Xi's are vectors of predictors, and epsilon I is the noise. And the standard method is to pick beta hat by regression. So I'm going to minimize a certain objective function. I'm sorry, I'm missing a sum sign here. And rho is a function. And the question is, how to pick rho. Okay, so that's, of course, an extremely classical question. There has been a lot of work on this, starting with Fisher in the 30s. In a slightly different context. And in stats, there has been enormous amounts of work, basically in the 70s and in the 80s, on the properties of this robust regression estimator. So names that come to mind are David Reles, who was a student of Anscombe at Yale. Peter Huber wrote a fundamental paper in the Annals in '72. Stephen Portnoy did a lot of work, Arno Mammon, Peter Bickel, and Yochai, and all these people. And the short answer is that it's easy. If you happen to know the density of the errors, and for the sake of argument in this talk, I assume I do, what you should do is take minus the log of the density of the error. So use maximum likelihood estimation, and that's the best you can do. Okay? And that's, I guess, something that shapes a lot of people's intuition about how to do efficient regression. Okay, and the remarkable fact is that that's independent of the design matrix X. Okay, so let's look at an example. Let's do it in practice. Here what I have are double exponential errors. Okay, so the density is e to the minus the absolute value of x, properly scaled so that it's a density. And according to what I just told you, in classical results and intuition, L1 should be optimal. Okay, so I'll tell you a little bit about the design later. So what I did here is I compared the performance of the L1 estimator, where I use as my loss L1, to the L2 estimator, okay, which is also OLS, ordinary least squares. And here I have a curve. I don't know if you can see the details, but that goes from 0.05 to 1.4. And here what you have is the ratio of P, the dimension of the predictors, over N, the number of observation. And that's a key quantity in the problem. And in some sense, the surprise is that, so when this ratio of performance of L1 over performance of L2, or amount of error in L1 versus amount of error in L2 is less than 1, that means that L1 performs better. Okay, and again, the classical theory tells us that L1 should perform better because we have double exponential errors. But what happens is that when P over N is greater than 0.3 roughly, suddenly least squares performs better. Okay, and so that's perhaps somewhat disturbing because, well, the previous result that at least shaped my intuition before doesn't seem to be very helpful in designing regression here. Okay, so there's a problem. It's interesting, and so what should we do? And again, now these things will depend on the design, but under some assumptions, so we're going to assume that the errors have a log concave density, and for the moment we'll assume that f epsilon is known. The point is basically, for reasons I'll explain later, it's a good idea to try this loss function. So P2 is a function that takes value x squared over 2. To this, you add the log of the convolution of a Gaussian density with a properly chosen variance with the density of the error. You scale that. You take the Fenchel-Legendre dual of this, and then you subtract P2. Okay, and R opt is this. So I'll explain where this comes from. And the claim is basically that this is optimal. And so before I go into that, and I won't have time to really go into the details of this, at least what we can do is, for double exponential errors, we can compute this numerically, and then we can look at the performance of that on simulated data, basically. So this is a comparison of this loss, this optimal, or claimed to be optimal loss to L1 against double exponential errors. So L1 should be the best you can do. If you have this classical intuition coming from the low dimensional setting. So here, it's 0.09, and what you see is that my, sort of quote-unquote optimal estimator beats the L1 estimator uniformly when P over N is less than 1 in my numerical experiment. Okay, so that's what I expected from the theory, but this is also verified in the simulations. And now I compared this optimal estimator to the least squares situation, and again, the ratio of the performance is always less than 1, so the estimator beats least squares. What you see that's also interesting is that P over N goes to 1. It seems that the performance of the two becomes essentially the same. And I'll give a little bit of explanation about this. Okay, so another thing I'll say is that this is for N equals 500, 1,000 simulations. It turns out, especially in terms of comparing L1 to L2, that you don't need N to be this large. But for this, the computations we did require asymptotics, basically where P and N are both large. Okay, so the aim of the talk is to understand these pictures and give you some idea of the phenomena that are behind. The caveat, I'll say immediately, is that this optimality picture, or this loss, is now very sensitive to geometric properties of the design matrix, and basically sort of somewhat hidden assumptions about the geometry of the xi's. Okay, so there's no hope, in some sense, in this context, to find the absolutely a loss function that's optimal independently of the design, because it's very easy, for instance, to come up with designs where what you're doing is basically a P one-dimensional regression. That's the case if your xi's have exactly one non-zero and all the others are 0. So here, optimality will depend on the design. Another interesting thing for me, I think probably also for a statistician, is basically the bootstrap seems to fail in this context. I give a bit of insight into that. And in this setting, there are lots of interesting statistical phenomena. And so I'm going to work always with this assumption that P over N is not close to 0. So one of the reasons for this is, of course, that we have large data sets, now many predictors, many observations too. But also the hope is that by doing this, even in low dimension, you're keeping track of higher order terms, okay? And so you're getting more accurate predictions than the classical things. Okay. So I'll tell you a little bit about the computation of the risk of robust regression estimators. Then I'll talk slightly about, shortly about inferential questions. What's nice here is that we don't have bounds. We have exact asymptotic results. So we can do asymptotic inference, basically. And then I'll talk about this issue of optimizing the risk with respect to the loss function, which is where this rho opt comes from. And then I talked about the penalized case shortly. I should say that some of the results here are not completely shown, or we haven't totally finished. Some we have finished, but I'll be a bit superficial about that. I hope that's okay. Okay, so how to understand the risk of robust regression estimators? So we need, unfortunately, a bit of notation. P over N is the ratio of the dimension of the predictors over the number of observations. At this point, we assume that that goes to a non-zero limit. That's between 0 and 1. And basically, under regularity conditions on the distribution of the errors and the loss functions, basically, the first result is that beta hat minus beta naught, the norm of that, the L2 norm of that, is asymptotically deterministic. Okay, and this we can show under assumptions that are much more general than normality. I put normality just to give you an idea. So we call our rho of kappa this limit. It depends on rho and it depends on kappa, the limit of the ratio P over N. And basically, to understand this limit, what you need to look at is this other random variable, z hat epsilon, which is epsilon, a random variable with the distribution of your errors, plus a normal scaled by r rho of kappa. Okay? And basically, what happens is that there's another deterministic quantity that appears, And basically, C and R row of kappa satisfy this system, this nonlinear system of equation. Okay? A key, a very fundamental role here is played not by the loss function, but what's called its prox. And so the prox is a concept that comes from this paper of Moreau in 65, which is about proximity and duality in Hilbert spaces. And basically what it is, the prox is the Moreau-Yosida regularized is f of y, the minimum of f of y plus an L2 term here, and basically this is the argmean for the Moreau-Yosida regularized. Okay, so it's a function, it's well defined, it's kind of nice. And there's another representation for the prox, which is actually the one that's more natural in our context, but it's a bit more complicated. Okay, we can do much more than this. We can talk about elliptical models. I'll say one thing. We can talk about heteroscedastic epsilon i's, weighted robust regression, and we really don't need normality for xi. To get the system, here at this point, we still need IID-ness of the entries of the xi, okay, and regularity. What's nice, too, is we can say a lot of things about the residuals. So we look at the residuals for the problem, okay? And in the asymptotic limit, the law of the residual, so in the standard case, it's basically the law of the errors, because you can estimate beta naught. And here it has not so much to do with the law of the errors. Basically, what you have to do is take what I call z hat epsilon before, so epsilon I plus an independent normal, takes the prox of this, and that's the law of the errors. Okay, so we estimate also very poorly the distribution of the errors in this context. It should be noted that beta hat is, of course, not consistent for beta naught here. Our row of kappa, which is the norm, doesn't go to 0. Okay? Nonetheless, when you project in a certain direction, you can still do inference. Okay? So really, what you should think of is that beta hat is orbiting around beta naught. I'll say a bit more about this later, on a sphere of a fixed radius, or an ellipsoid in certain settings. Okay? So this is all very different from the classical setting of P over n close to 0, and we basically can't use the techniques there. So another important question is to understand, so before I said the xi's were normal or the entries were IID, and you need to understand a bit the sensitivity to this assumption. So a standard thing that comes also from, for instance, for me, the work I've done on random matrices, is to look at elliptical models. So you look at the normal, this curve, or script xi here is a normal covariance identity, and lambda I is an independent random variable. Okay, and the idea is that if lambda I is independent of script xi and the expectation of lambda I square is 1, this xi still has covariance identity. Okay, and so basically when you do this perturbation of the model, you can still come up with a system of equation in two unknowns. You still have that beta hat minus beta naught is asymptotically deterministic, but the system is very different. Okay? And so basically the point of studying this is to understand a bit the sensitivity of the results to the geometry of the data set. And I'll say a tiny bit more on this later. Okay? So how do the proof and the heuristic work? It's quite technical, especially when you do everything rigorously, but basically the key element, what is used all the time, is concentration of quadratic forms in script xi. What I mean by this is that if I look at the quadratic forms in xi, so xi transpose m xi, where m is a fixed matrix, this is essentially equal to its trace, and it's deterministic. The consequence of this is a bit problematic, because if you take for m the identity, that means that the norm of these vectors is essentially constant. So, you know, essentially this means that you're working with data sets that live near spheres. Okay, so the point of ellipticity is when you have a lambda I here and they're random variables, you're breaking this sort of spherical assumptions about the predictors, and what you see is that when you break this assumption, then you change the result. Okay, so that's why I say that the result is very sensitive to the geometry of the data, and in particular, there's no universality. You can't expect that the distribution of xi won't matter. What matters is not the details of the distribution, but more the geometry of the data set. We use a lot of leave one out ideas, martingale ideas, and basically make a connection with random matrix theory, specifically spectral distribution for random matrices and convex analysis. It wasn't obvious at all that it was the prox everywhere, but once you know it, it's kind of easy to verify, but maybe hard to find. And that was a bit of a surprise, at least for me, because in L1 regression, we know that many residuals, for instance, are exactly equal to 0, p of them. So it didn't look like a random matrix problem, more like a combinatorial problem, but actually it's a random, you can tackle it through random matrix techniques. Okay, let me say a little bit about inference issues. Basically, when xi's are IID normal 0 sigma, then we have a very nice and completely elementary stochastic representation for beta hat that tells us that beta hat, if the true beta naught is beta naught and I have covariance sigma, is the truth, plus something where I solve the problem for beta naught equals 0 and the covariance is identity, times sigma minus a half times a uniform on the sphere of radius 1 in RP. And what's very important is that this random variable is independent of this one. Okay, this is just very simple invariance. So what that means is that it's easy to handle the case where beta naught is not 0 and where sigma is not the identity. The same sort of stuff work in the elliptical setting. And what's very important is that you see V transpose times this U is normal. Asymptotically, that's essentially obvious. And so it's possible to do inference about V transpose beta naught based on V transpose beta hat, because you basically pick up the truth plus a normal whose variance depends on this quantity, beta hat rho 0 identity. Okay? It's also not complicated to include an intercept. There are several manners to do that. And a side note about the bootstrap, basically, if the bootstrap worked, and you have this sorts of stuff, that would put a very strong constraints on the value of beta hat star minus beta naught, beta hat star being your bootstrapped estimate. And basically, unless you're in a very, very specific setting, it cannot be, this constraint cannot be satisfied. Okay? So this is the setting where when you bootstrap both the predictors and the responses, and essentially you're doing weighted regression there, and that's why you're changing the structure of the problem significantly. Okay? But what I want to say is that the quality of the inference you see depends only, essentially, on beta hat rho 0 identity. Okay? Because that comes out, when I multiply everything by V transpose beta hat, this is the only thing that depends on rho, basically, that's left. And so it's natural to try to optimize this R rho kappa, which is the limit of this quantity over rho. Okay? All right, I also want to say, and I'm going a bit fast, is that optimality here can be measured in any sort of norm. For instance, if I look at LQ norm for Q different from 2, the stochastic representation I mentioned before immediately says, basically by independence of this random variable and of this one, and the fact that the thing scales linearly with a constant, that the expectation of the LQ norm is just the expectation of the L2 norm of beta hat rho 0 identity, plus something that depends basically on the angle of your estimate, where now the LQ norm appears. But this is clearly, if you're trying to optimize over rho, the only thing that matters is basically the expected value of the L2 norm of the error. Okay? So it makes a lot of sense to estimate this R rho kappa, and you get optimality in any norm if you can do that. Okay, so how to do this? Recall the system. I had z hat epsilon is an error plus R rho kappa times z is a normal 0, 1. And I have this complicated looking maybe system of two nonlinear equations. And the problem too is that rho appears here, but it's also hidden in the distribution of z hat epsilon. But it turns out that we can still optimize R rho kappa over rho. Okay, and what we did is we wrote the problem as a feasibility problem in R, which R are possible. And then the fundamental thing is really this result of, again, it's in the 65 paper of Moreau, the fact that any point, and it could be, it's true also in vector spaces, can be decomposed by, basically the prox of rho evaluated at x plus the prox of the dual Fenchel-Legendre dual of rho at x. Okay? And so basically, it turns out that the natural way to write the system is to express everything in terms of this prox of rho star. Okay? And so that's a natural variable for the problem. Then you can do a Cauchy-Schwarz that gives you a lower bound on the possible values of this quantity, r square I epsilon of r, okay, where that's the Fisher information of epsilon plus rz. Okay, and once you have this lower bound, what you do is you come up with an optimal rho star that saturates the inequality. Okay, and then what you have to do is go from the space of proxies, which is a nice space, to basically go back to the space of loss functions. Okay, so that's at the high level how it works. And so that's how, following this strategy, it's important that minus log f epsilon be convex. Otherwise, the guess we had wasn't a prox. But basically, that's how we come up with this guess. Okay? And r opt is the minimum of that. So that's how we came up with this loss function. Some remarks about this. For Gaussian errors, see, for Gaussian errors, the convolution of two Gaussian is a Gaussian. So L2 is still optimal. So if the errors are Gaussian, basically the best you can do is least squares, okay, even in any dimension. When P over n goes to 1, you can measure the performance of any loss functions, and so you realize that the performance of the, against the least squares estimator performs asymptotically optimally when P over n goes to 1. Okay, so actually OLS has lots of very nice properties. However, the limit of the optimal loss is not L2. And also this rho opt proposed here is convex, okay, which is important. Okay, so here's a plot. This is for P over n is 0.5, double exponential errors. What I've plotted here is L1 here. So, okay, that's the classical theory of the setting where P over n goes to 0 tells us that that's the optimal loss to use. In blue here, you have the thing we proposed, okay? And in red is least squares, and black is minus the log density of this z hat epsilon, okay? And actually, when you think about it, this optimal loss, at least for double exponential errors, is a bit like the Huber loss. It's not the same, but it's a bit like the Huber loss function, okay? All right, so what about the penalized case that allows us to do work when p is greater than n? This was all p less than n. The techniques can handle that too. At this point, what we need is a sort of separable penalty, something that acts on the coordinates of beta separately, and the covariance of xi is the identity. It's possible to characterize the limit of beta hat minus beta naught. I'll show you how, what is the result. And there's also work on related things in the case of lasso, but we had general loss and general penalty of Donoho, Maleki, Montanari, and Bayati, Montanari, at least that's what I've seen. But the approach here is different from what was done here, for instance. Okay? It's kind of horrible, but basically what happens is that instead of having a system of two equations in two unknowns, so this is the one I really care about, like the norm of the error, the L2 norm of the error. Now the key quantities are this norm, nu of tau, which has a meaning in the problem, and this c of tau, okay? And the point is just to say that where we can come up with a system, again, the key thing is not the prox of the loss or the prox of, it's not the loss or the penalty, it's their prox, okay? And basically there's also this nice representation for the distribution of individual coordinates of the beta, which is the prox of the penalty evaluated at the normal random variable that has the true mean and a certain variance, okay? And it's a prox at k tau, which is related to the parameters of the problem. So basically, once you have this, you can come up with a system of three equations in three unknowns, and you can at least numerically you can solve. And what we've done is to check that our predictions match the simulation. I haven't finished the rigorous proof of that, but okay. What's nice about this is because we have a measure of risk, an exact measure of risk, we can ask, well, can we do the same thing we did before, which is find the optimal loss in certain setting? And so basically what happens that in the case of Tikhonov penalty or L2 penalty, it turns out that the optimal loss is again in the family of losses we found before, which wasn't canonical for us, at least at the beginning. But it turned out that the optimal loss is still in this family. Now, the optimal R is different, okay? It satisfies this equation. And you can also find the optimal amount of penalization you need to add. Okay, so this is all assuming the somewhat unrealistic thing that you know the distribution of epsilon. And we're working on doing this in a sort of adaptive fashion, meaning that we adapt to the data and to the unknown distribution of epsilon. But what's nice is it tells us that this family of loss functions, at least when you're interested in L2 problems, is kind of natural. It appears, well, now 2 places, so oops, that's more than one. Okay, so in conclusions, what we saw here is a bit the interplay between loss function and error distribution in high-dimensional robust regression. It wasn't obvious, at least at the beginning of the project, that we could get that. This optimal loss function is computable in high dimension. It has a pretty close form representation, a simple formula, which we can implement. And the key thing is that it's not maximum likelihood, okay? So when P over N is not close to 0, the optimal thing to do is not maximum likelihood, at least in this design context. And it turns out, at least in simulation, that even when N is not very large, maybe N is 50, we see sort of similar pictures in terms of L2 starting to beat L1 when P over N is not very close to 0. What's very nice too is that it's possible to do inference in this context. Okay, we don't have bounds, we have asymptotic fluctuation behavior. There are problems with the bootstrap. I haven't talked about them in much details, but when you bootstrap, even the norm of beta hat minus beta naught, your bootstrap estimate of this is not consistent. So it's really, one needs to be wary. And I worked a lot on the L2 case in a strictly random matrix context, and there are the same problem there. So that's a bit of an issue. We can do penalized regression, and this optimal loss is kind of, in some sense, it's somewhat natural because it's optimal not only for unpenalized regression, but also in this sort of Tikhonov or L2 regularized context. And with this, I'll thank you for your attention.
Thank you very much.
Yeah, so the question is does the model give results for LP norms? And it does, but in some sense, it's not super satisfactory because there I used the normality of the design. Okay, so because I had rotational invariance, the LP norm aspect of the measure of the quality is thrown into basically the behavior of the angle, and not so much of the norm. Okay, so sorry, I'm going to bring back the slide. So what I said, and that's a question, we can get this for any LP norm, but that's really tied to the Gaussian design, and I can't do this rigorously, even when I can compute or show that the result holds for the L2 norm of beta hat. I can't show that this result extends to the LP norm if I have a non-Gaussian design. What happened is the rotational invariance of the Gaussian design is key. And that's what gives me the separation, the independence between basically the norm of the error and its angle. And so I expect that in sufficiently high dimension, similar phenomenon will happen even if I don't have a Gaussian design, but I haven't shown it. Does this answer your question?